So this is the Chapter 1 PowerPoint for AP Chemistry. It's going to focus on matter, measurement, and problem solving. First, we're going to start with a discussion about what is chemistry. Chemistry is the science or the study that seeks to understand the behavior of matter by studying the behavior of atoms and molecules. The most difficult thing about chemistry is we cannot see the majority of what we're studying. We're going to study very, 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 very small pieces of matter called atoms and molecules that are what we call submicroscopic. You can't even see them with a microscope. The closest we've gotten is with an electronic tunneling microscope, and even then we really have not seen an atom. Like you can see a cell, for example, under a microscope. So what we do with chemistry is we study what we can see, and we use that to explain the things we can't see. So for example, if we see a fire, if we see a flame, if we see a specific color, we use that macroscopic observation to try to explain what's happening submicroscopically. And that's really what's most difficult about chemistry, is you cannot physically see very clearly what's happening at the atomic level. So the first thing, obviously, the key to all chemistry is an atom. An atom is very similar to a cell in biology, where a cell is the basic unit of life that still retains the properties of life. An atom is the basic unit of matter that is still considered matter. It is basically the smallest fundamental unit of matter. Atom is made up of a proton, neutron, and an electron in differing amounts depending on the type of atom. You can see by the picture here that the nucleus of an atom has mainly protons and neutrons, where the electrons are orbiting around the nucleus. We're going to look at these two pictures and kind of the difference between the two. You can see they're very different graphical, showing an atom very different graphically, but we're going to see why one is more correct than the other, but why we still kind of keep, for example, the one on the upper left, the kind of one that looks like a solar system one around. You can see the orbitals shown in the one on the right, and we're going to talk about what those orbitals mean, and we're going to define an orbital a little later. A molecule is any combination of two or more atoms, and you can see some examples here. So you see a molecule at the top, all the ones at the top, the hydrogen, oxygen, nitrogen. Those are what we call the diatomic gases. And remember that the prefix di means two. So a diatomic gas is simply a two-atom gas, an atom made up of two atoms. A molecule made up of two atoms of the same gas. There are 7 diatomic gases. They are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Those are the 7. And they cannot exist by themselves in nature. If they exist by themselves, they are very unstable. And you can see the molecules at the bottom are made up of 2 different kinds of atoms. We have water as a classic one, nitrogen dioxide, etc. You've probably heard about the scientific method on almost every science class you've taken, and there's a very good reason for that. It's kind of the heart of scientific study. It's the heart of experimentation. You may see these steps listed in a different way, but the 5 basic steps are observation, hypothesis, experiment, data collection, and conclusion. So when we talk about observations first, that's kind of gathering information. You see something first, and then you use an experiment to try to explain it. There are 2 main types of observations. Qualitative, you see the word quality in there. That talks about a physical characteristic, the size, the shape, the color. Quantitative has the word quantity, which means a number. So quantitative observation is 5 grams, for example, or a measurement. They are both equally important in an experiment. Sometimes you can only have qualitative observations. You cannot record any measurements. Sometimes you only have quantitative. At best, you have both, but they're both equally important data and observations in an experiment. Your hypothesis is your educated guess. That's maybe how you've learned it in the past. What we say is it's a falsifiable observation. It's something you can disprove. If you can't disprove it, then that experiment has actually given some evidence to proving that theory. Usually a hypothesis is a statement. It used to be a question when you were little, but a statement is really the way you want to list your hypothesis in this class. The experiment is what you're actually conducting. There are variables, the independent variable, the dependent variable. Remember, the independent is the one that you change. The dependent changes in response to the change in the independent. The classic is the plant one. You have a plant in the light, plant in the dark, and you're measuring how tall it grows. The amount of light would be the independent variable. The height of the plant would be the dependent variable. Things called controls also exist in an experiment, and those are the things you attempt to keep constant. So basically you have a point of comparison. Data collection is very important. Data, again, can be qualitative or quantitative. It's important to organize your data in charts and graphs so that it's easier to see the trends in data. And finally, conclusion is the conclusion from your experiment. But if you're able to make multiple conclusions that are proven again and again, you may have a scientific theory or law that can come about there. Scientific knowledge is empirical, and it's based on observation and experimentation. Scientific knowledge is based on fact, is pretty much what that statement says. We infer from the data, but for the most part, in science, we are going to have clear-cut proof that what we say is true. We're going to go over the phases of matter. You can see that it represented with pictures up here, a gas, a liquid, or a solid. The phases of matter depend on the order of the particles and the arrangement of the particles. So for example, in a solid, the particles are very closely packed. They vibrate in space. They are very ordered. They're very close together. And the opposite end of the spectrum, in a gas, you have total disorder. There's a lot of empty space between the particles. The particles are moving in constant random motion. And then a liquid's kind of in the middle. There's some disorder. The particles are in clusters. They're free to move, but they're kind of closer together than they are in a gas. Heat and pressure can change something from one phase to another. Classic is, of course, ice melting and freezing. That's a temperature difference. But actually, pressure can also do that. That's how you get liquid O2, for example. That's how you get oxygen in a tank for you to use later. Plasma is actually a gas wherein the electrons have separated from the atom. It's a superheated gas where the electrons are free flowing. Plasma is the sun, lightning, those kind of things are plasma. It's a very, very superheated gas. There's two types of solids. Basically, there's the crystalline solid and the amorphous solid. And you can see from the picture, a crystalline solid is very ordered. The particles are in a very orderly arrangement. This is where we're going to get things like gemstones and diamonds and glass and those kind of things that have very ordered arrangement. The amorphous solid, you can kind of think of it like a blob. Amorphous solids are things like plastic, things that you can curve is an amorphous solid. The organization of matter chart is something, again, you've seen probably a lot. Matter is anything that has mass and takes up space. It is most things in the universe. And then we further separate matter into a pure substances or a mixture. A pure substance it's only made up of one type of thing. A mixture is two or more. An element has a single type of atom. A compound has two or more types of atoms. And then you have a homogeneous and a heterogeneous mixture. Homogeneous is a solution. It's when the properties are the same throughout. And a heterogeneous is where you have more defined properties in different parts of the mixture. Mixtures are separated using something called separation techniques, and they take into account the physical and chemical properties of the substances in the mixture. Things like manual separation, filtration, distillation, chromatography, decanting, centrifugation, there's more. We're going to go over each one now. This picture here shows you a couple different types of separation techniques. Decanting is shown up here on the top where you have the stirring rod covering the beaker where you're just trying to flow out the water. You're going to try to attempt to keep the solid in the middle. This takes into account the difference in size and shape of the particles, the difference in solubility of the particles. You see here a funnel set up with a piece of filter paper. That's obviously filtration. That's going to help you keep more of the solid into the filter paper. You may, with filtration, want to keep the solid or you may want to keep the liquid. It depends on what you're looking for in the particular experiment. You see a distillation setup here. Distillation takes advantage of differences in boiling points, and it allows you to separate liquids from other liquids. So you can see here you have the substance boiling, and then you're going to have something called a condenser tube, which basically the liquid, whatever you may be, mostly it's water. Once it reaches 100 degrees, the water will evaporate. It'll go down the condenser, and it'll turn back into liquid water, and you've pretty much had pure water here with the distillation process. This is especially useful with oil, for example. Oil has a very high boiling point, so you can separate oil and water very easily with this substance. Shown here is chromatography. This takes advantage of two things, the solubility of substances and kind of the weight of the substance. This is where you have the classic experiment with the dye, and you submerge it into the chromatography chamber and you get the dye separating. This again is decanting. What you're trying to do is attempt to keep the solid in the beaker, but let the liquid flow down the stirring rod, as you see shown there. This is centrifugation. This is used a lot in blood type things when you're blood typing or you're doing blood tests. Basically, it separates things according to weight. So the heavier things, it's kind of like the gravitron. The heavier things will go to the bottom, and then as you go up, the lighter things will be at the top. All chemical changes are accompanied by energy changes. We're going to see those paired up a lot throughout this course. Energy and work are two things we're going to talk about. They're different in chemistry as they are in physics. In chemistry, energy is kind of looked at in terms of making and breaking of bonds, and the work done is the bond breaking and the bond making. Whereas in physics, we're talking about moving a car distance, but in chemistry, it's a very, very small energy change. It's a very, very small work done. And then we have potential versus kinetic energy, and again, you can relate that to chemistry, where the potential energy is the energy contained in the bonds, and the kinetic is what happens after you break the bonds, the energy that's released. Remember, the law of conservation of energy says that energy cannot be created or destroyed, it only changes form. This is the whole idea that the energy of the universe is constant, and it's basically just recycling throughout itself. So, for example, if you have a bond broken in an experiment, usually somewhere else, that energy that was released is then used to make something else, and so on and so forth. The energy just cycles through. We're going to talk a lot about units of measure, and this may be review. Hopefully it is review for you. You can see the SI units here. Remember, SI is the scientific system of measurement that we use. We will now use all of these different units, so it's good for you to know them. This is something you should memorize. This should go on your memorization list. Just a couple notes. Notice masses base unit is actually a kilogram. That's because a gram is so small. Kilogram is actually the base unit. Temperature is measured in Kelvin, and you can see the other units of measurement there. This is something you should memorize. The SI unit, the SI system, the reason why we use it is because it uses multipliers of 10 to convert, which makes things very much easier than, adding or multiplying by a very weird number in the standard system. A derived unit is just simply a combination of base units. Best example here is speed, which is meters per second. Volume is meters squared, so it's meter per meter per meter. And density is going to be kilograms per meter cubed or grams per milliliter. An intensive property versus extensive property. You're going to remember that intensive is independent of how much is there. And extensive is dependent on how much is there. So an extensive property is basically anything you measure. That's going to be something's weight. It's going to be something's volume. Where an intensive property is something that it doesn't matter whether you have a drop, a cup, or a gallon. So things like density, boiling point, melting point. And actually, intensive properties are usually used to identify substances because it doesn't matter how much you have, it's going to be the same. Best example is the density of water is exactly 1 gram per milliliter. It doesn't matter how much water you have. If it's 1 gram per milliliter, you know that's pure water. So again, density is going to be huge. We're going to use it again and again and again. You do not have to memorize density of things, although the density of water pretty much should be in your brain by now that it's 1 gram per milliliter. Density is equal to mass divided by volume, and the units of density kind of differ depending on what mass unit you have, what volume unit you have. Remember that a milliliter and a centimeter cubed are equivalent, so you can just substitute one of those for the other. Density, what you can use with density is it tells you whether something floats. So something will float if it's less dense than the medium it's in. This is a classic density column, they call it. You have a bolt at the bottom, and then you have different liquids, honey, corn syrup, maple syrup, milk. You have even, a cherry tomato in there, beads, ping pong ball at the top, and it just shows you that with different densities, things can actually float on each other. When we talk about reliability of measurement, we are talking about sig figs, and what sig figs tell you, significant figures, is how accurate or how precise your measuring tool was. So it's kind of like how much was it calibrated to. Now the reason why sig figs are kind of going away is because we're using digital things, and digital equipment do not have sig figs. They just report out however many decimal points you have. But when you have other things like your graduated cylinder, you got to look at how many decimal places is it actually calibrated to, and then what's my guess digit. So exact numbers have no uncertainty and thus have an unlimited number of sig figs. Again, that's something with the digital scale. Other things like counting objects, defined quantities, integral numbers, those kind of things. The significant figure rules are here. Basically, it has a lot to do with the zeros. Anything that's not a zero is always significant. Trapped or interior zeros are significant. Leading zeros are not significant only if there's a decimal point. and the trailing zero rules are there. These are just something you should get in your head, you should memorize, but remember, when we report sig figs, you're going to use the number of sig figs it's calibrated to plus a guess digit. When you're using measured quantities in numbers, in problems, and this is where you're going to see the most in AP Chemistry, the result of the calculation must reflect the precision of the measured quantities. The general rule is you should not gain or lose precision during a mathematical operation. You're going to look at your textbook for rules for this, but a good kind of rule to live by is your answer should not be more precise than your least precise measurement. So if you have measurements, 10 that go to 4 decimal places, but then that last one only goes to 1, you really should only report your measurement in 1 decimal place. Again, when you measure using sig figs, it depends on, these rulers are very different. This one's only measured to the meter. This one's obviously measured down to the millimeter, etc., and so forth. So the more precise your instrument, the more decimal places you can report. This has to do with accuracy and precision. These targets are great for this. Accuracy is how close you are to the actual value. Precision is how close you are to other numbers, so how common your numbers were. Obviously, we want our data to be here. We want them to be accurate and precise. We want them to be very close to the actual value and very close to each other. There's certain other things that these other types can tell us. So for example, if it's not accurate, not precise, the numbers are all over the place, we have a lot of error. We have both systematic and random error. Remember that systematic is the equipment error, random is human error, and if we have these kind of numbers all willy-nilly, you have both. If you get numbers that are accurate but not precise, so they're very close to the number, but they're not close to each other, that usually tells you there's a lot of random error. There's little things that were done here and there. Whereas if you have numbers that are not accurate, they're not close to the real value, but they are precise and they're close to each other, that usually indicates systematic error. There was something wrong with the equipment. It wasn't calibrated correctly. The substance used wasn't correct. The molarity wasn't correct. That can tell you a lot when you look at these accuracy versus precision numbers. When we solve chemical problems, we're going to use dimensional analysis, we're going to use conversion factors, and we're going to use some specific steps for solving. We're going to really kind of sort our data, make a strategy of how we're going to solve it, and then go back and check. And we're going to do some practice problems that involve these things. If you remember, factor label method is the tic-tac-toe boards. You want to make sure that your units are opposite so that you can cancel out. We're going to use this for almost everything now, not just converting units. We're going to go from molecules to, candelas and those kind of things with all these conversion factors. So it's important for you to remember this. We will practice this in class. And that is the end of the Chapter 1 lecture.